Okay, we're going to list directory contents. There's no directory contents. We're going to do touch card. So we didn't open an editor or an application. We didn't give any contents, yet we have a file. So what did touch actually do? Let's step back a second. Most of us use touch as a tiny file creation command. You might go touch main, touch readme. This is the kind of thing I'd do. I'd just sketch out a project, but that's not quite what touch was originally for.
You can't touch this.
It touches an existing file by updating its access and modification times. So change file timestamps. Update the access and modification times of each file to the correct time. That's useful for build systems and scripts. So say you have foo.c and you have a make file, then make will realize that foo has been updated and will build it again. It's also quite useful with marker files. You just put an empty file in a place, something like that, or touch, I don't know, migration complete. And in some systems you have that and the contents of the file doesn't matter. The existence of the file is the state. Every time we touch. But the behavior I'm interested in is this. Empty directory, touch card, it's there. So I said didn't use an editor, no application needed, didn't need to give any content. So how does that work? So this is the source code of the touch command. Okay, so it starts off with a license, some authors, some includes, the name of the program, some constants, set up some flags. And this is the bit we're interested in now. At the core of it all is this touch function. Try to open file, creating if necessary. So it's not messing about. So this fd open takes the file path that we've given it, and it's got various flags. So this is the line that matters here, and you see it has ocreate here, and that means if this path name does not already refer to a file, then create it. So touch is not doing some special create empty file operation. It's saying open the path, and this flag says create it if necessary. If we dig through the file descriptor reopen, there are loads of wrappers and interfaces, but you end up with the operating system's implementation of open, which is called path open at. The kernel allocates this struct file. It's a runtime object representing a file. Let's say we have a more complicated path, so touch. And this bit here is a while loop, and it's walking each part of the path. Is there any more? Yep, there's that. Is there any more? Yep, there's that. Is there any more? Oh, we found the actual end of the path. We open it with open last lookups. So with open and create, then we lock the inode. Pause there. So what's it doing? So we've asked it to create a file called card.md, and it's locking the directory that it's in. So you might think it's going to go create file, lock the new file, but no, it goes create file, lock the directory that will contain the file. So why? D entry is a directory entry. So this is an important thing. So the D entry is the metadata about the entry in the directory. The kernel's representation of a name in a directory. So this inode is the metadata about the file. So we've got the D entry, which is the metadata about the directory entry, i.e. the name of it and where it is. And then this is the inode, which is about the file. So we are connecting the directory entry, which contains the name of the file, to the inode, which is the metadata about the file. So we're putting the file and the directory together.
You can't touch this.
So what we saw there is when we run touch, we do open with create, we then acquire an exclusive lock on the parent directory, we allocate an inode, we add the directory entry, and then we connect the name to the inode. That was the key part that we just showed in the code. The file name is not stored inside the file. The file name lives in the directory. So it's the directory entry which maps the names to the inodes. The file name is not stored inside the file. The file name lives in the directory. So when Linux creates card.markdown, it edits the parent directory and adds a new mapping so that card points to the inode. Now the weird line in the code we saw makes sense. Now this weird line makes sense. Linux locked the directory because creating the file means changing the directory. The new file needs a name, and names live in directories. So we make a new file and we update the directory entry. Let's follow the arrow across from the name to the index node. The index node is the file system object behind the name that stores the metadata for the file. So Linux's runtime representation of it is just a struct, simple struct. So the inode is the file system object behind the name. It stores the metadata for the file. So the inode is the file system object behind the name. it stores the metadata for the file. Owner, group, permissions, timestamps, size, link count, references to other blocks. This is much closer to what people mean when they say the file. But even the inode is not the file context directly. For a normal file with content, the inode points to data blocks. When we do touch card.markdown, the size is 0. There are no bytes of content yet at all. So what got created with touch? Not content. The important new things are the directory entry and the inode. The directory gives a new file a name, and the inode gives the file an identity and metadata. The data blocks come later when something writes actual bytes. So touch, when we create it, makes an empty file and updates this timestamp in the inode metadata and gives it a name in the directory entries. So touch is tiny, but it's shown us the shape of a file system. Names live in directories, metadata lives in inodes, the content lives in the data block. There's a lot of machinery hiding behind this 5-letter command, and that's why we're learning the shell at deeper level. Not because employers want us to memorize commands that we'll forget by next week, because behind each command there's some elegant engineering worth understanding. And once you understand the models and the engineering, the commands become inevitable. So what we can see is that there's this higher level interface where everything is simple and everyone's running around swimming and eating fresh fruit. And then there's the actual elegant engineering underground that you never see with the inodes and the directory entries. Okay, so we have the directory entry on disk, which maps the card to the inode number. And then we have the index node itself, which stores the metadata from the block pointers. The owner, permission, size, timestamps, block pointers, etc. Then the Linux kernel creates a struct D entry, which represents the directory entry. And then we have the struct inode in memory, which represents the inode while it's in use. And then finally, we have our hero, the file, which we get with open, and it represents an open file. And that's what the kernel and programming languages and shell commands they use. The file and directory shell commands, they all call these operating system primitives like open, and it does all the steps for it underneath. So the commands in the shell and the file and directory standard library functions are used when programming in C++ and Python are both wrappers around the same operating system primitives. Once you understand those primitives, the shell commands stop feeling like cryptic puzzles that you have to memorize. They become different ways of asking the kernel to do the same small set of jobs. That's why we're learning the shell this way. Not as a list of commands, but as a window into how operating systems really work. If you've got questions, or there's another command you'd like me to take apart like this, leave a comment below. And if you'd like to learn the shell from first principles rather than by memorizing commands, subscribe, because that's what this series is about. I'm also covering Python and C++ programming and software engineering more generally. If you want to keep watching, there'll be another video up here. So until next time, have a good night.